Okay, welcome everyone. So I'm so delighted because Scott Aaronson is here today. So he is a computer scientist at CSAIL, and basically he's super awesome, which is why I wanted him to be here. So I first heard about him because when he was very young, I don't know how young, but he wrote this piece suggesting a big number championship where like two people would try to write down very large finite numbers. And as he points out in the article, that turns out to be a much more interesting exercise than one would think. And it turns out to be connected to interesting issues in computer science. So, I knew about him for a while. And then I realized that he was a professor at MIT. And not just that he understands philosophy. So he is like the perfect person to be a bridge between computer science and philosophy. And then the third thing is that he is an expert in quantum computation, which is amazing. So my objective for today is basically that it be fun and interesting. What I was going to suggest is that he start by telling us about just efficiency. So what that means, and then if he's up for it, to talk a little bit about quantum computation.
Okay, awesome. So thanks for inviting me here. Class sounds like a lot of fun. Paradox and infinity are two things that I really enjoy. So today I wasn't planning to really say much at all about infinity, unless someone asks. I was just going to talk about really, really large finite things and the difference between, just merely very large finite numbers and, unbelievably large finite numbers. So that's, and that's a lot of what we're concerned about today in theoretical computer science. So I understand from Professor Rayo that you talked about the proof of unsolvability of the halting problem. So you've seen Turing machines, you've seen all that stuff. So so that was, I regard the stuff that Turing and that Church and that Gödel, and Post and Queenie, I guess, did in the 1930s as, this phenomenal foundation of computer science, and as a really, really nice warm-up to what I see as the real questions. Basically, what they did is that they studied the question, for what types of problems is there a computer program, that will always halt and give you the right answer, right? And and they found that first of all, it is possible to give a pretty good definition of what you mean by computer program, something that's already not obvious, right? Like when I first learned programming as as like an adolescent, I thought that I've seen BASIC, but if I see, C, if I see a more powerful language, I'll be able to write programs that I could never write in this other language. Okay, it's not the case at all, right? Every programming language that gets over this one threshold, this threshold of Turing universality, is equivalent in power to every other one. Okay, so that's an amazing fact. And that, that's the thing that really allows us to have a mathematical theory where, where we just talk about what's computable and what isn't. And, and within this theory, we can prove that, a massive number of things are, that we might like to do are computable. We can also, prove that there is a single, it is possible to create a single Turing machine that will simulate any other Turing machine if you just describe that other Turing machine to it on its tape. Right, Turing proved that in the 30s. I like to call that the existence of the software industry lemma. Okay, so that's a pretty important result. That's why instead of having 300 different types of laptops on our desk, one for email, one for video games, one for this and that, we can usually get by with one, sometimes two, but just for convenience, right? And okay, but then on the other hand, Turing, and Church also proved that there were problems that are not computable. Okay, like the halting problem. Okay, and now to be clear, it's you can't prove as a mathematical theorem that something can't be solved in the physical universe, right? It is conceivable that tomorrow someone will, come up with some magic box that has a black hole inside of it or something, and they'll say, look, this box solves the halting problem, and you'll just feed it examples, and you'll never come up with a counterexample, and eventually you'll say, I guess this box solves the halting problem, right? But even then, what we would know for sure would be that box would definitely not be a Turing machine, okay? Whatever's inside it, definitely goes beyond a Turing machine. And over the last 80 years, I think we've accumulated a lot of evidence that actually anything that the actual laws of physics of our universe seem to describe, seems to be simulatable by a Turing machine to whatever finite precision you like. Okay. Now, there are some caveats in that statement. You could say there are lots of things that are just unpredictable in practice, like the weather. But you could say that the unpredictability of these things is just sort of a function of not being able to measure the initial conditions to a high enough precision, right? You don't know the exact state of every air molecule in the sky, and for that reason, you can't predict the weather, and beyond, let's say, a week, into the future, if then, and in fact, even if you did know them to, unlimited precision, still, ultimately quantum effects would be relevant and would get amplified because of chaos, and so you could only ever hope to predict the probability distribution over, rain and sunshine and so forth, and not, and still not know exactly. Okay, but. What we mean, in saying that sort of the Turing machine seems to capture everything is that if you were to specify the initial state of the system, well enough that the system itself will reliably do the same thing, so you can reliably prepare the system in the same state, and then it will produce the same output, over and over again, then a Turing machine, suitably programmed, will be able to produce that same output with this, just as reliably. Okay, and so in that sense, could say, all of the physical laws that we know about, seem to be sort of mappable onto a Turing machine. Which is a sort of an astoundingly bold claim. And some of you might have heard that, Roger Penrose, for example, believes that it's false. He thinks that, the human brain can't be a Turing machine, and therefore the brain has to be sensitive to quantum gravitational effects, which would not be captured by a Turing machine. So that's a bold speculation. I think it's fair to say that almost no one else agrees with the arguments that lead him to it. Okay, but at least he sort of recognizes the sort of thing that that would have to be true in order for something like the brain to not be captured by a Turing machine, right? When people say, oh well, the brain is not a Turing machine because it's made out of meat, and a Turing machine is made out of silicon or something, right? I think that's a misunderstanding. First of all, a Turing machine is made out of paper, right? But it doesn't, from the point of view of computability, it doesn't matter what the thing is made out of, right? What matters is its, logical relationships. Okay, so that was all, I think it was a very beautiful story. Both, the extent of what Turing machines can do, also what they can't do. But now, when people started building actual computers, in the 50s, the 60s, let's say, what they realized was that the theory of computability was sort of not, even asking sort of what came to be sort of the most relevant questions. Okay, and the reason is that the sorts of things that people would think of to do with their computers, almost all of them are computable. Okay, it's like it doesn't it doesn't that often occur to us to even, ask our computer to solve the halting problem, right? Maybe because we just know in the back of our heads that it's uncomputable, so we scale down our expectations. Okay, but a huge number of things that we want to do are computable, but they may be computable, but only with a number of steps that completely explodes in our faces, so that to get an answer, right, so that like the universe will have gone cold, the sun will have burned out, the entire universe will have degenerated into black holes and radiation before your computer program would have barely even started. Okay, so and so what people realized is that if your problem is computable, but only in that sense, only in the sense of your program will halt after a googolplex years, after quadrillion years. Okay, then that's not a very useful type of computability, right? And what we really want is that we can get an answer in our lifetimes. Okay, right, and so then you might have said, okay, fine, that's kind of obvious, right? It's not like Turing was unaware of the issue, right? I mean, Turing worked during World War II on breaking the Nazi Enigma code, right? And and apparently his biggest contribution there was speed improvements, right? There were some Polish mathematicians who had figured out in principle earlier, how to break the thing, but it just wasn't practical enough to sort of decrypt the messages and get it within enough time that it's still actionable intelligence. And Turing, figured out how you could like eliminate, one letter from the search process and so speed it up by a factor of 26 or so. Okay, that made a huge difference. Okay, so of course people knew about, an efficient program is better than an inefficient one. Okay, but you might have thought that but fine, this is just an engineering issue, right? This is just an issue for the practical programmer to worry about, or even Turing, should only worry about it while he's, wearing his code breaker hat, not while he's wearing his theorist hat, right? You might say, because after all, the speed of a program is not the sort of thing that has these, these beautiful invariance properties that computability has, right? The same program might be slow on one computer and fast on another one, right? It could depend on the hardware. It could depend on all kinds of crufty little details. Okay, but in fact, so this brings me to what was discovered in the 60s, I'd say, and really solidified in the 70s. Okay, which is that in fact there is a very important sort of dichotomy, tells you something about the speed of a program, and which is really, really independent of a particular computer architecture, right? You find the same phenomenon, which is really, really robust across. It doesn't matter if we're talking about a Mac or a PC or an iPhone or an Android. Okay, there's this distinction between like P problems and NP complete problems, things like that, which is still just serenely unaffected by all of that stuff. So the sort of thing that we worry about in theoretical computer science for the last 40 or 50 years, let's say, is what's called computational complexity. Okay, and well, the key trick, the key sort of step that we make in order to get sort of mathematically nice questions is that instead of asking about how many specific steps does your Turing machine take before it halts? Like, is it 1 million steps or is it 2 million steps? Right? That's just a question that's a type of question that tends to not have a very theoretically satisfying answer, right? Because it could depend on are you talking about a 1-tape Turing machine or a 2-tape Turing machine, or are you talking about does it have a 2-symbol alphabet or a 3-symbol alphabet, right? It could depend on all kinds of little details like that. Okay, so what we do instead is that we look at the scaling behavior. So by that I mean we look at At what rate does the running time of the Turing machine increase as you give it larger and larger inputs to deal with? Yeah.
So I'm actually not familiar. What's a two-tape Turing machine?
Oh, okay. So, so you can, you may have learned about Turing machines that have one tape and that have a tape head that moves back and forth on the tape, reading and writing symbols. Okay, but you can take this basic notion and you can generalize it in all sorts of different ways. So, for example, you could have a Turing machine with a tape head and with pointers into two tapes. Okay, this is sometimes convenient, like for if you want to have one tape that stores the input and then another tape that has scratch space. So then that way your Turing machine doesn't have to keep shuttling back and forth on the same tape to read, write. It can just be reading on this tape and it can be doing all of its scratch work on this tape. Kind of like, if you get an exam, right? It could be nice to have like some blank paper in addition to the test, so you don't have to, write on the official test, right? So, okay, and you can do other stuff. You could have a two-dimensional Turing machine, okay, so that it actually looks like a piece of paper rather than just like this thin strip. You could have a three-dimensional Turing machine. If you're a string theorist, you could have an 11-dimensional Turing machine. Okay, and one of the things that really justified the Church and Turing's definition of computability is that all of these things can be proved to be equivalent to each other. Okay, by equivalent, I mean any language that any one of them can decide can also be decided by any of the others. Okay, and the reason for that is simply that with any of these types of Turing machines, you can create an emulator for any of the other types, right? This is sort of what it means for them to all be over the threshold of universality. Okay, so if you had your favorite language, which was decidable using a two-tape Turing machine, and you wanted to decide it using only a one-tape Turing machine, I could let you think about it for yourself as an exercise if you wanted to. How would you actually do the simulation? I'll give you a hint. The simulation is allowed to be horrendously inefficient in terms of time. Okay, you might, in order to simulate a single step of this two-tape machine, you might have to shuttle back and forth and do lots and lots of bookkeeping work over on this one-tape machine. Okay, but I claim to you that you can do it. Okay, so I'll leave it as a challenge for anyone who wants to think about it. So okay, but there were certain questions about now if we're interested in the amount of time that it takes, let's say the number of steps that it takes to decide your language, rather than just is it decidable at all, then it actually could make a difference, which of these models we're talking about, right? As I hinted at before, the same language might be decidable much more quickly using a two-tape Turing machine than it is using a one-tape Turing machine. Actually, let me give you an example of that. Okay, so a famous example is palindromes. I don't know if you discussed this, but okay. So there's a question. You have a string written on your Turing machine tape, like this, and you want to know you want to check if it's a palindrome or not. Is it the same backwards and forwards? Okay. So there's a standard way to do this, using a one-tape Turing machine. And basically, the thing that you do is you look at the first symbol. Let's assume that it's just a string of A's and B's. Okay? If you look at the first symbol, you store in your memory. You make a so let's say that I'm going to put a special stop symbol over here. Okay? So now I'm going to let's see. I'm going to store in my memory that the first symbol was an A. I'm going to overwrite this A with a stop symbol. And now I'm going to go all the way to the end of my string until I find the stop symbol. Then I'm going to go one backwards, and I'm going to make sure that there's also an A here. If there's not, then my string is definitely not a palindrome, right? If it is an A, then I'm going to overwrite this with a stop symbol, and then I'm going to go back until I hit the stop symbol. Then I'm going to go to the right. Now I see that there's a B here. So I'm going to store a B in my memory, right? And I can store like a single bit in my, just sort of on the head, right? Just in which state do I go to? Okay, so I'll store in my tape head that there was a B here, overwrite it with a stop symbol, go here, go back, and then check that there's also a B here. Okay, now this works, right? This is one of, when I teach 6045, which is my computability and complexity class, so I can hereby advertise. Okay, so this is like, I think this is the one example that we do of a Turing machine. So there, I've sneak previewed it for you. Okay, and after that we just talk much more abstractly about okay, look, just pick your favorite programming language and think in those terms, and then you could compile it down to Turing machine if you really wanted to, which you don't. That's the whole beauty of universality, right? That you don't have to think in this low-level way. You can, okay, but now I want you to notice something interesting about this Turing machine. Okay, let's say that I gave you a string with n symbols in it. Okay, I'll call it x1 up to xn. How many steps does this Turing machine take, to finish, like as a function of n? Roughly. Okay, and I don't care about the exact value. I just care about, roughly how does it depend on n? Is it like n cubed? Is it like 2 to the n power? Does anyone see? Yeah.
Does this depend on, is it just going to be going linearly, or is it going to be depending on what the Turing machine actually does?
Well, it's going to depend on what the Turing machine actually does. I'm interested in the number of steps that the Turing machine takes. And let's assume that the string is a palindrome, because that's going to be the maximum amount of time, right? If it's not a palindrome, then it may stop earlier, and realize that.
Will be n squared?
Yeah, exactly. How come?
Because you're going back and forth.
Exactly. That's exactly right. Because this thing zigzags back and forth and back and forth and back and forth, it's actually to decide whether an n-bit string is a palindrome, it actually takes, as we say, order of n squared steps. Okay, and so this is this is not as efficient as you could hope for, right? The most efficient that you could hope for would be order n steps, right? You definitely couldn't hope for less than that. Why not?
So you at least have to read all of it.
Yeah, exactly. You better read the whole, right? I mean, like let's say that the whole string was a palindrome except for one mismatch, right? You've got to read the whole string in order to find that mismatch. So okay, so we know that n is a lower bound. We know that n squared is an upper bound. This Turing machine solves it in n squared steps. It's actually possible to prove that any one-tape Turing machine must use n squared steps to solve this problem. That's not trivial. Okay, that takes a little bit of work, but one can actually prove that. Okay, and by the way, that's a pretty rare situation. Usually in computer science, we have no idea how to prove lower bounds. Okay, we only know how to prove upper bounds. Okay, you've heard of the P versus NP problem. That's an example of that. Okay, but in this case, we actually do know how to prove that a one-tape Turing machine needs n squared steps. Okay, if on the other hand you have a two-tape Turing machine, then I claim that you can do better. Does anyone see why? Okay, so let's say that now I have an extra scratch tape. So I still want to know if my string is a palindrome, x1, x2, up to xn. Now I have this extra scratch tape in addition. Yeah?
So you can basically copy down your string to the scratch space, and then check the original string forward as you check the scratch space backwards.
Perfect. Yes.
And so all of those operations are just proportional to n. So your overall thing is proportional.
Exactly. That's perfect. Yep. So yeah, as long as I've got one scratch tape, then I can solve this problem in linear time. And this, I think turns out to be the sort of optimal result, right? You can simulate a two-tape machine by a one-tape machine, but possibly with a quadratic blow-up in the running time, okay, as exhibited by this example. Okay, so so this is an example that, if we care about the exact scaling behavior, that can depend on, exactly which type of machine you have. On the other hand, if you look at, any of the machines that we actually use in practice, so PCs, Macs, iPhones, whatever, right? They all have something in common, which is they all have what's called a random access memory, right? They can all, you can just put into the chip, into the registers. I want to access this memory location, and then you go out and you get it, right? So random access machines tend to be much more tightly related to each other. They tend to be able to simulate each other with almost linear time, reductions. Okay, so in any case, we could fix one of these machine models, and now we could talk about scaling behavior. So the question that will interest us is, we want to get at sort of the, what is the inherent difficulty of our problem, right? Not on this machine or that machine, but sort of what is the sort of inherent, hardness or easiness of the language we're trying to decide. We'll assume that the language is a computable one. So it's just a question of how many steps do you need. Okay, and so the way that we quantify this usually is by saying, you're given an input string, x. Okay, and so on the horizontal axis will be the number of bits of x. That's usually a convenient way of measuring the size of your problem. Just how many bits does it take to specify the input? There are other ways to do it also, but that's usually a convenient choice. Okay, and so then on the y-axis, what we'll be interested in is fix an optimal Turing machine. So fix one that sort of solves the problem in the asymptotically best amount of time. But then for that machine, look at the worst possible input of each length. Okay, look at the worst possible one, and then we'll look at we'll let t of n be the worst number of steps that the optimal machine needs on an input of size n, and we're interested in at what rate does t of n grow as a function of n. Okay, so if you have a linear time algorithm, then it grows like that, right? That's pretty good. That's often the best you can hope for. Sometimes you can even do better than linear time. Like if you have some random sampling algorithm, right? Like if, let's say, you want to take a statistical poll, right? You just want to know, like, what does the U.S. population think of, legalizing marijuana, right? To within plus or minus 2% error. Okay, you don't have to poll the entire U.S. population to know. There's a sublinear algorithm, right? In fact, you just call people at random, and in fact, the number of people you need to call doesn't even depend at all on the size of the population. It only depends on how confident you want to be in the result. Okay, that's the magic of polling, right? So you could have that would be like a constant time algorithm, way down here. You could have you could have a quadratic time algorithm, which would grow like that. Okay, that's still not too bad, right? Then so let's okay, but then you could have an exponential time algorithm. Okay, and exponential is really the kind of thing that we're afraid of. Okay, because exponential and above is really the type of behavior that can lead to this blow up I talked about earlier, where you have like a real life problem instance, and then you get the result that your computer needs longer than the age of the universe to find the answer. Okay, now in principle that could also happen with polynomial, right? Like you could have an n to the 10,000 algorithm, right? And that's formally a polynomial amount of time. But if n is greater than 1, right, then that's already hopeless. Okay. Conversely, you could in principle have an exponential amount of time, but which is perfectly fine in practice. So you can have 1.00001 to the n power. Right, and for any reasonable sized n, that's going to be pretty good. Okay, but what justifies focusing on this polynomial versus exponential is that in practice, these things just don't show up that much. Okay, in practice, usually if you find, if your problem is solvable by a polynomial algorithm at all, then empirically it's usually solvable, in time n or n squared or n cubed, or the biggest that we ever tend to see in practice is going to be something like n to the 10, n to the 20. Okay, but even in those cases, usually like if there's an n to the 10 algorithm that's discovered for some problem, it usually just means that you didn't think hard enough about the problem, right? And if you thought about it more, you could get it down to n to the 8, and then someone else could get it down to n to the 6, and and so forth. Okay, whereas if your problem inherently requires 2 to the n time, then it's probably just a general purpose efficient solution is going to be too much to hope for, right? And you're going to have to do something else, like either just give up, that's one option, right? Or settle for an approximate answer, or settle for a heuristic algorithm, which doesn't always work, but which the particular cases that you're dealing with, might be easier than the worst case. Okay, so then you could handle them. Okay, so you'll have to do something like that. Okay, so when does when do these sorts of exponential running times occur? So usually they occur when you have some giant combinatorial space of possibilities and you're trying to search through it. Okay, like for example, I give you a map with a bunch of countries and I ask you to color each country either red, green, or blue, but so that no two neighboring countries are colored the same. Right, so you can start red, green, blue. All right, this one is actually pretty easy. Green, okay, but all right, so far that was pretty easy. Okay, but now you could imagine that I have situations where there's a choice. I don't know, should I color this one green or should I color it blue, right? So you can make complicated scenarios, right? Or just imagine a Sudoku puzzle, or in fact a Candy Crush, right? Or or Minesweeper. Okay, any of these puzzle games where you have you can reach a point where it's not clear which move should you make, right? And the number of possibilities can just explode combinatorially on you. Okay. Or if you want a really hard example of this, right? Imagine just programming your computer, just find me a proof of the Riemann hypothesis, right? Something like that. Okay, that that sounds completely different, but there is a sense in which it's really no different than the Minesweeper example or the Candy Crush or whatever. Okay, which is certainly if I ask for a proof of any length, then that's an uncomputable problem, right, in general. That's, follows from the unsolved, it's equivalent to the halting problem, actually. Okay, but now what I could do is I could say, look, I really only care about proofs that are a billion symbols or fewer. Okay, I really only care about proofs that are up to n symbols long, right, written out in some formal system, like, first order logic and, ZF set theory, whatever. Okay, so then, now I obviously have a computable problem, right? Which is that I just want to know, is there a proof of, at most n bits in length, let's say? So obviously there are at most 2 to the n such proofs, right? And obviously, for each one, I could have my computer check, is it valid or not? Actually, most of them will just be random gobbledygook and will just be obviously invalid, right? But I could just have my proof. I could just have my computer, iterate through every possible string of n bits and check whether any one of them is an encoding of a valid proof of my question, like the Riemann hypothesis. Okay, that's certainly a program I could write. Then the only problem is then I run it and then I don't see it stop before the universe goes cold. Okay, because this is a 2 to the n complexity, right? So. Okay, so let's see. So So the rough way that we classify things is that we consider the set of all problems that are solvable in by some Turing machine that runs in polynomial time. Okay, and that class is called P. Okay, so P. So by the way, this is all happening within the set of computable problems. So what I'm talking about right now is like the various tiny subsets of the set of all computable languages. Okay, so a language is like a set of strings. Okay, and the setting is your Turing machine is provided with one of these strings, and then it has to halt after some number of steps and decide and accept if your input string is in L and reject if it's not in L. Okay, and so if there's any Turing machine that does that at all in any amount of time, then your problem is in this computable class, which is so huge that I can't even fit it on the board. Okay. Now, if moreover there is a Turing machine that does this, and that always, on an input x, it always tells you whether or not x is in L, and using a number of steps that grows at most like the length of x raised to some fixed power, then we say that your language is in P. Okay, that's the class of problems that have polynomial time algorithms to solve them. Okay, so there's actually a lot of interesting examples of things that are in P. I mean, first of all, almost anything that we normally do with our computers, like adding, multiplying, dividing, all that stuff is in P. Right? Multiplying takes n squared time if you do it by the grade school method. Turns out that there are actually much more clever ways to multiply two n-digit numbers that actually take close to linear time, like n times log n times something else, log something. Okay, so they rely on the fast Fourier transform. Okay, so so often like the first way you think of to do something is not the fastest way, right? That's what makes this field I mean, that's why it's been going on for 50 years, right? So multiplying matrices. Turns out that like if I give you a collection of men and women, and I tell you like who is willing to go to the dance with whom, and you want to pair them all, you want to know, can I pair them all off so that everyone is happy with their partner? That problem is in P. Okay, that's called the matching problem. Right, that one sounds on its face like that would require an exponential search, but it doesn't. There's actually a much more clever way to do it that avoids the exponential search. Okay, it turns out that actually, even if it were same-sex couples, that's a more complicated algorithm, but that's again in polynomial time. Okay, determining whether a number is prime or composite. That we now know to be in P. That was actually proved in 2002. The primality problem was shown to be in P by 3 guys in India, 2 of whom were undergrads at the time. Okay, which in this solved, right, I guess like a 200-year-old open problem, right? Something that Gauss had thought about. Okay, and the original algorithm that they came up with for primality testing was n to the 12, and then that was since brought down to n to the 6. Now, as it turns out, as wonderful as that was, right, it didn't matter that much in practice because since the 1970s, we've had very, very fast algorithms to tell whether a number is prime or composite. We've actually used those for key generation and cryptography. Okay, the only problem is that those algorithms were randomized. Okay, so they required the use of random choices. And for that reason, they went a little bit outside of P. They were actually in a somewhat larger class called BPP, bounded error probabilistic polynomial time. Okay, by the way, I like to say that if we were physicists, we would have given everything much cooler names, like quark and black hole, and we're stuck with P and BPP. Okay, but nothing I can do about that. So primality, determining if a number is prime or composite, was known for a while to be in this class, and in fact, even by an n-cubed algorithm, right? Which is really quite practical. And anytime like you have to generate a Kerberos key, and it says like please wait a few seconds while we generate your key, right? It's running something like this n-cubed algorithm to do that, okay? Okay, and then what was proved 12 years ago was that in fact the primality problem is even just in P. Now there's a far-reaching conjecture that many of us believe today, which says that actually everything in this BPP should be in P. It says that everything that has a randomized algorithm one should be able to de-randomize it and replace it by a deterministic algorithm. Okay, this would follow as long as we could have good enough pseudo-random number generators, and we could prove that the numbers that they generate are always sufficiently indistinguishable from real random numbers, right? Most of us believe that that such generators exist. We even have candidates. We just can't prove that they always work. Okay, so there's this P, BPP, and this contains lots and lots of interesting stuff. Okay, but then the other really important class to discuss is NP. NP stands for non-deterministic polynomial time. Okay, and what this NP is it's the class of all the problems where they might be, it might be really, really hard to find an answer, but at least if someone claims that the answer is yes, then there is some polynomial-sized string that they can give to you to convince you that the answer is yes, and you could check that person's work in polynomial time. Okay, so it's you have to wrap your head around it a little bit, right? And it does not, by the way, it does not stand for not polynomial, okay? So in fact, all of the P problems are also NP problems. So P is contained in NP. So it's best to illustrate with an example, okay? I told you that determining whether a number is prime or composite is in P, okay? But there's actually, an important property of the algorithms is that if they tell you if your number is prime or composite, but if it's composite, they give you no clue what the prime factors are. Okay. Now, if you actually want to know the prime factors, that we think is a much harder problem. Okay. So that one is factoring. And by the way, it is extremely important for modern cryptography, both that primality testing is in P, that's what lets us generate the keys, and also that factoring should be a hard problem, right? Anytime you order something online, your credit card number is protected only by the belief that factoring is a hard problem. It's also protected by many much less solid beliefs than that, like that no one made a C, buffer error, okay, which as we learned last week, is not a safe assumption, okay, but But the sort of the core of modern cryptography is, most of it is based on our belief that problems like factoring are hard, okay? Because, the way that it works is that, you want to order a book from Amazon. So Amazon, has this public and private key, okay? They send you the public key. The public key is the product of two huge prime numbers, right? The private key is the factors. Okay, so we have some huge number, and it's a product of these two prime factors. And then the way that these crypto systems work is that you encrypt your credit card number or whatever using using the public key, using the product, but in such a way that hopefully it can only be decrypted by someone who knows the prime factors. Okay, and if these prime factors are both, let's say, hundreds of digits long, then you make the assumption that anyone who only knows n and not p and q is not going to be able to factor this. It's just going to take them too long. Okay, again, it's obviously a computable problem, right? Just start trying all the possible divisors until you hit the right ones. Okay, but you make the assumption, which might or might not be true, that that it would take them longer than the age of the universe. Okay, so that's how most of our cryptography works. Okay, so now something to notice about this factoring problem is that, although it might or might not be exponentially hard to solve, if someone, said to you, I know what the prime factors are, there is a very easy way to tell whether that person is lying or not. Okay, you say, great, so show me, show me the factors. They give them to you, then you can multiply them, right? Or at least your computer can, okay? You can, easily have your computer multiply these numbers, check that, they really do multiply to n, and then by using the fact that primality is in P, you could even check that P and Q are prime numbers, that they can't be subdivided further if you're suspicious of that part. Okay, so for this reason, we say that factoring is an NP problem. Okay, now factoring is a very special NP problem, because in fact, not only does it always have a solution, every number has a prime factorization, right? There's always a unique solution, right? Every number has exactly one prime factorization. Okay, Euclid proved that 2,300 years ago, right? Okay, but not every NP problem is like that. If I gave you a jigsaw puzzle, or I gave you, like a partially solved Minesweeper, right? There might be many ways to solve it a priori. There might be no ways to solve it. Okay, but if there is a way to solve it, then you could just you could convince someone else of it by just showing them the way that you had, right? Similarly with the map coloring, right? It might be really hard to color a map. In fact, it might not even be possible to do it. Like the map of the continental U.S., you can't color it with 3 colors. Okay, that's that's known. Okay, but if someone claims to you that their map can be colored with 3 colors, then they could convince you of that by just showing you the coloring, and then that coloring you could check in linear time. Okay, so for this reason, all of those sorts of problems are in this class NP, in this class of checkable problems. By the way, if someone claimed to you that their map is colorable with 4 colors, does anyone know how hard would it be to say whether that person's right or wrong? Yeah.
You probably do it in constant time.
Yes, that's correct, because that person would always be right. Okay, now at least if the map is drawn in the plane, so like you don't live on a planet that's shaped like a donut or something like that, right? But you live on a spherical planet, and the countries don't go like over or under each other. They're just on a flat surface. Okay, then it was proved in the 70s that every map can be colored with only 4 colors. Okay, so that's so there, and furthermore, a 4 coloring can actually be found in P. That's also known, in n cubed time, something like that. Okay, if you want to know, now again, if you want to know whether your map can be colored with 2 colors, that's also an easy problem, because you just pick one country, let's say pick a color for it, doesn't matter which one, let's say red. Okay, then everything that neighbors that has to be colored black, and everything, let's say the other color, and everything that neighbors those black countries has to be colored red. And everything that neighbors those red countries has to be colored black, and so forth. And if doing so, like your hand is forced, right? And if in doing that you ever run into, you're ever forced to color 2 neighboring countries the same color, well then your map was not 2 colorable, otherwise it is. Okay? Determining whether your map can be colored with 3 colors, that no one knows how to do efficiently. Okay? So in fact, this 3 coloring problem belongs to a huge class of problems, which in some sense are the hardest problems in NP. They're called the NP complete problems. Okay, so basically a problem is called NP hard if any problem in NP can be reduced to it. So for a problem, okay, this takes some thinking about, but for a problem to be NP hard, what it means is that if I gave you a magic box that just solved this problem, so problem A, then you could and you knew that it solved problem A, then you could use that box to solve any NP problem in polynomial time. Okay, by just appropriately transforming your problem into problem A. Okay. That's what it means for a problem to be NP hard. So it's like at least as hard as any NP problem, you know, in that sense, in the sense that any NP problem is reducible to that problem. Okay, now a problem is called NP complete if it's both NP hard and in NP, and itself in NP. So the NP complete problems are like the maximal problems in NP, or the hardest problems in NP. Okay, and huge discovery in the 1970s is that thousands and thousands of natural NP problems actually are NP complete. Okay, so 3 coloring is an example. Actually, Minesweeper, Super Mario is an example. Theorem proving, you know, lots and lots of things of more practical importance, industrial optimization, and so forth. So factoring is not known or believed to be NP complete. In fact, if it is NP complete, then some very bad things would happen. Okay, we don't think it is. So factoring may lie in this intermediate zone between P and NP complete. All right, now in the last minute, I'll tell you about quantum computing. So a quantum computer is a computer that would exploit the fact that at the subatomic level, there's actually not only is nature probabilistic, which would take you up from this P to BPP, but the probabilities are calculated in this really, really strange way. Okay, I don't know if any of you have taken 804 or whatever, right? But if you know, until while you don't look at a system, its evolution is governed by something called the Schrodinger equation, and the Schrodinger equation involves these complex numbers, which are called amplitudes. Okay, and an amplitude is not itself a probability, but it's related to one. Okay, so each possible event has some amplitude, say alpha, that it will happen. And if you want to know the probability that the thing will happen, then you have to take the absolute square of the amplitude, is the rule. Okay, but now if the same thing, like let's say a photon hitting a certain place on a screen, if it could happen one way with a positive amplitude and a different way with a negative amplitude, then those two ways can cancel each other out so that the thing doesn't happen at all. Okay, and you just see a dark place on that screen where there's no photon. You close off one of the slits, and then the amplitude is positive or it's negative, and so then you do see it there. So you can decrease the number of ways for something to happen and thereby increase the probability that it happens. That's quantum mechanics in 1 minute. Okay, so everything else in quantum mechanics is more and more, instantiations of that one phenomenon. So, so a quantum computer is a computer that would exploit, this sort of, rules of probability, so that you would try to choreograph things so that the different amplitudes leading to each wrong answer would be some positive, some negative, so they'd mostly cancel each other out. Whereas the different amplitudes leading to the right answer should be either all positive or all negative, so that then when you measure, right answer will be seen with high probability. Okay, so now you can once again give a complexity class corresponding to what can you do in polynomial time with a quantum computer, with one that uses these principles. This one is called BQP, bounded error quantum polynomial time. And what was discovered 20 years ago was that BQP actually contains the factoring problem. Okay, so if you could build a quantum computer, then you can break almost all of the cryptography we use. You can factor numbers efficiently. On the other hand, contrary to a common misconception, BQP is neither known nor believed to contain these NP-complete problems. These may still be hard even with a quantum computer. Quantum computer might give you some small advantage for them, but we don't really know how much yet. We'll probably have to build a quantum computer and test it out before we really know. So, all right, I'm out of time, so I'll stop there. Thanks.
Thank you so much.
Yeah.
So Wednesday's class will be relatively important because it'll be our dry run for the proof of Gödel's theorem. So you don't have to come, but it would be a good class to come to.